The next transformation in the understanding of energy came from James Joule. And James Joule represents an extremely interesting story because his father and his family before him brewed beer for a living. He wasn't a professional scientist, but it turns out that James Joule had remarkable insight because he recognized that the mechanical energy of a system was equal to the potential energy plus the kinetic energy, as we've just described. But he also realized that he could isolate the potential energy term and write that the energy, the mechanical energy of position, was equal to mgh, which is to say the change in mechanical energy as a body descends is equal to mg delta h. And so the mechanical energy release is a question he thought about, and he said, I can build a machine, I can build an apparatus that converts that mechanical energy into heat. This was a brilliant move for the following reason. He created this machine with two masses, and as those masses descended, they rotated a shaft that went into a steel enclosure that contained water, but it also contained paddles linked to that shaft. And so as those masses descended, those paddles rotated, and they converted that energy into the heat of the water through the intrinsic friction between the paddles and the water. And why did he do this? Well, he recognized something very important, and that is that he could measure the change in the thermal energy of those molecules by measuring the temperature change. And in fact, he could write the equation that change in thermal energy resulting from those paddles sweeping through the water was equal to a constant times the change in temperature. And that constant is equal to the heat capacity of the system. And the system then referred entirely and explicitly to the machine, the paddles, the water, and the shaft going into it. And he had a frictionless bearing there, so all of the heat that he was capturing inside came directly from the rotation of those paddles. So he said, all right, I know what the mechanical energy is. In fact, I know what the mechanical energy release is. The mass times acceleration of gravity times the height that those masses fell through in converting that mechanical energy into the intrinsic internal energy of the water and the metal in that box. Now, he put a thermometer in that box so he could measure the change in temperature. The key aspect then was that the heat generated, which we will call Q, was equal to the heat capacity of that machine times the change in temperature. And that meant that he could equate mg delta H with the increase in the temperature of that system. So we have mechanical energy on the left-hand side, we have heat on the right-hand side, and this equation represents the mechanical equivalent of heat. And what that did was it set energy on an absolute scale. And that's why the energy unit today that we use is called the Joule, because he could relate directly that change in temperature with the change in mechanical energy put into the system. And remarkably, he built these systems with extremely long run lengths for the mass descending to convert that mechanical energy into heat. And he actually measured the absolute temperature scale to better than 1% with these systems. This was a profoundly important step forward, and that's why we call today the energy unit the Joule. But it also opened up all sorts of other capabilities, because if we shine sunlight through an opening in the top of this same system, and we use a mirror and we focus the flow of light, of electromagnetic radiation, onto that same system, we've calibrated the energy against the mechanical mg delta H. But that means that we can write and we can calibrate the change in electromagnetic energy with exactly the same system. So we can intercalibrate mechanical energy and electromagnetic energy. The next thing we could do is we can create a heated filament, put it next to the bottom of this device, and again determine exactly how much electrical energy was flowing through by virtue of the fact that those electrons are colliding with a higher resistance filament, releasing heat, and we can calibrate electrical energy against the same absolute scale by simply measuring the increase in temperature of that system as a result of that heated filament. And then finally, we can take a Bunsen burner and we can burn natural gas, CH4, and direct that flame into the bottom of the same system, and we can measure chemical energy with exactly the same apparatus. And that means we can couple mechanical energy to electromagnetic energy, to electrical energy, to chemical energy, all with the same system. But Joule and his experiments pointed out something remarkably important, and that is that if I look at mechanical energy, electrical energy, chemical energy, and electromagnetic energy, those are organized forms of energy, all of them. Organized energy is what we always strive to have because that's the useful form. And it's also referred to as macroscopic energy, and we'll see why the relationship between organized energy and macroscopic energy takes on a very important role as we unfold all of these aspects of the concept of energy. But what Joule did was he recognized that these organized forms of energy come down to disorganized forms of energy. And by disorganized forms of energy, we also mean microscopic forms of energy. And these are microscopic forms of energy because they relate to the molecular motion within the body to which we've added, for example, heat. So if we view any body as a sequence of masses coupled by springs, which basically are what chemical bonds are, as we take these organized forms of energy and we raise the temperature of the system, we're simply raising the kinetic energy and the interactive energy between the molecules within that body. And so it's that molecular motion that increases in its intensity and increases the measured temperature of that body, and that increase resides primarily because we've converted organized forms of energy to disorganized forms of energy. And as we'll see when we study thermodynamics, it's easy to convert organized forms of energy to disorganized forms. It's much more difficult to convert disorganized forms of energy back to organized forms.